is Filimonov. I'm from Moscow Institute of Physics and Technology. And today I'd like to speak about security systems. There are a lot of security systems everywhere nowadays. In airports, in government buildings, even in this hotel there is a security system. But how can you make sure, how can you be sure if the security system does its job? How can you design an efficient security system? And the more important question is, how can you prove that your design security system is correct? Today I'm going to speak about a method of efficiency evaluation of physical protection system. First of all, I'd like to mention the goals of our research. We have studied several approaches to efficiency evaluation of physical protection systems, and our study reveals that there are two main problems. You must develop a model of movement through the defended facility or defended territory, and the second problem is threat detection probability. You have to somehow create a method to calculate where intruders are detected. Although there are some existing approaches, but further research is needed, and our work is focused on such research. Before we can proceed to these problems, I should define more accurately the physical protection system, what it is. A physical protection system combines people, equipment, and procedures that make it possible to protect assets or facilities against various kinds of threats. There are different threats in modern world, but there are two main types of threats. Human threats, these can be thieves, vandals, or more generally intruders. Or industrial threats like fires and even earthquakes. An efficient security system must detect a threat, and it should be designed in a way that makes it possible to respond to a threat and neutralize it in time. So, the security system is considered efficient if it can detect a threat and give enough time to security forces to respond to a threat and to intercept an intruder. So if an intruder coming from any direction can be intercepted by security forces, then the security system is efficient. But if there exists some kind of attack route where security forces cannot intercept, they don't have enough time to intercept the intruder, then the system is inefficient and doesn't suffice for its purpose. So, to analyze a security system, we need some model of this security system. In our research, we model a territory, a protected territory, as a field of square cells. The size of the square, a single square, determines the accuracy of the analysis. The smaller is the square, the more accurate calculations can be made. But we need more computation power with small squares, of course. Each square has a number of parameters. These parameters correspond to average characteristics of area of protected territory that falls within the square. For example, if there is a wall in the territory corresponding to the square, or it's just a road. And the main parameters are square delay time, the time that one needs to move through the square. This delay time will be considerably higher for walls than for just roads. And another parameter is detection probability. Detection probability is the probability of being detected while moving through the square. These parameters are devised from the plan of protected territory, the structure of security system like movement sensors, door locks, and of course these parameters depend on intruder abilities like movement speed or locking distance. For example, if you are a skilled intruder, you can reach the door faster than unprepared. Thus, we have a model of kind of facility, and movement through the territory is modeled as like jumping between adjacent squares. So delay time shows how long you have to stay in the square before you can perform the next move. This model is good for planar analysis, but usually security systems deal with buildings which have several layers, multiple floors. So we need to modify the model a little bit to apply it to the three-dimensional movement. We make special lift squares that correspond to staircases or lifts, actually. And these squares, like normal squares, have 8 adjacent neighbors in the planar level, and 2 more connections to the upper and lower level, or 1 connection to the ground level, for example. Thus, the model allows movement in third dimension. As I mentioned before, the system is considered effective if security forces have enough time to intercept an intruder. So we need some kind of path-finding algorithm to find the best routes, the most vulnerable routes, and protect them. First, I'll briefly mention existing path-finding algorithms. Then I'll introduce our modification of a wave algorithm and show how it can be applied to a security system efficiency evaluation. Of course, there are a lot of path-finding algorithms. We know them from graph theory, like LEED algorithm, big straight algorithm, or R-star algorithm. However, they've been developed to solve a more general task in graph theory, and they have to be modified to be applied to a security system. So we've developed an adjusted wave algorithm. And it's like a kind of like Lee algorithm and kind of wave algorithm with following important modifications. First of all, each square or sphere in this figure represents have different delay time. We use discrete notion of time, so there is a minimum time unit delay time, and all squares have several time unit delay time. So if the square has more than time unit delay time, we replace it with a number of squares with single time unit delay time. So we make more uniform grid in terms of different delay times. Uniform again. We have making these corrections, we have a uniform grid squares. And of course, we need to use connections with upper and lower levels, as I mentioned earlier. Thus, after we have again a uniform field, we can use wave propagation, calculate wave propagation through this field to find actual vulnerable routes or fastest path from one point in the territory to the other. This is an example of applying the algorithm to a security system evaluation. Here you can see the wave spreading from the starting location in all directions. The characteristics of the field determines how fast, how far the wave front spreads. And after each time unit seconds, the area marked with green grows, and when the wave front reaches the tangent object, then you can see that we have found a vulnerable route, or the shortest path from starting location to the tangent object. Here is the more elaborate example of a real study. We put several starting locations on the perimeter so we can find more accurately vulnerable routes. And here you can see that green or red lines are fastest routes from starting locations to the tangent object. Analyzing these routes, we can see where our system is efficient. For example, here you can see that there was a door, a very strong door, so now nobody went, no intruder is going to go through this door, but here we see the window, which is rather unprotected. So this is a drawback of the design of this particular security system. Applying the model to the three-dimensional space, you can see we added 2 more floors and put the touch object on the third floor. And thus, the same algorithm can be used to calculate paths from the ground floor to the touch object using these squares. That's for movement. Now we can use our method can be used to calculate fastest paths from that location to tangent objects and determine how much time does intruder need to get to the destination. But then we need to determine starting locations. And here comes the threat detection probability problem. Firstly, I'll introduce the notion of normalized discrete logarithmic probability. Then I'll show how it can be used to calculate area of guaranteed detection. And after that, I'll give a simple example. Let the P with the probability of being detected in a particular square. Using several simple transformations, we introduce the notion of discrete logarithmic probability KP. There is a more accurate definition in our paper. But the main idea is that we move from complex computation to simple addition. And this new logarithmic probability behaves exactly the same way as delay time. And so we can use exactly the same algorithm to determine the threat detection probability. Let me show an example. Here different color squares represents not delay time like in previous figures, but detection probability. Using the wave propagation algorithm, but using logarithmic probability instead of delay time, we can find squares where intruder is detected with predefined probability. Because we are moving from one square to another square, we just add some more detection probability, logarithmic detection probability. And here we can determine the boundary of the area of guaranteed intruder detection. So here in the green area we cannot detect intruder with guaranteed probability, but after the boundary we can say that yes, here the intruder is detected with a probability of 99%. Then we can use this boundary as a standard location for our calculation of vulnerable groups. Using the described methods, we have developed a software which can be used to create a model of defended facility, to calculate vulnerable routes, to calculate the most efficient response for security forces, and thus perform an efficiency evaluation of a security system. Well, to sum up, we have developed a method and an algorithm of calculating the efficiency of a security system. And we define efficiency as an ability to provide enough time for security forces to intercept the intruder after the intruder has been detected. This method has been applied to evaluate efficiency of the security system in one of the nuclear power plants in Russia. It was a success. We believe that our research and security system faculty will help create better security system and make the world a better place. Thank you for your attention, and I'll be happy to answer your questions.
You mentioned the time to detect the intruder. Is there any standard time, like 20 minutes or 10 minutes? Is there any standard?
This time heavily depends on the configuration of the facility. So you need enough time you need to give security forces enough time to intercept the intruder. And the best way to intercept the intruder may be intercepting him or her after he is being detected at the on the path to the object we are protecting. And there can be no standard time for this because the configuration is always different. But if there is a route where security forces cannot intercept the intruder, physically can because they don't have enough time, the intruder may use this route to complete a successful attack.
And how we